Good morning and welcome to this week's Mathematics for Architecture lecture. We've finished our geometry topics and then we're moving on to a new type of mathematics. We're going to cover 3 topics in discrete mathematics. We're going to cover combinatorics, which is a fancy way of saying counting. We're going to cover probability and we will cover graph theory. Today we will talk about combinatorics and we're going to start probability. Next week we will conclude our probability, and then in the following lesson we will talk about graph theory. Our first topic for today is basic counting principles. And we start very, very easily. Let's suppose we have 2 sets, set A and set B. And let's suppose we want to count the number of elements in the set. The number of sets in A, we call MA, number of elements in A. NB is the number of elements in B. And A intersection B is the number of elements which are in both A and in B. And A union B is the number of elements in A union B, or to say it another way, the number of elements which are in at least one of the sets A and B. And we start with this formula. The number of elements in A union B is the number of elements in A plus the number of elements in B minus the number of elements which are in both A and B. A very, very easy example to start with. Let's suppose Ali has 3 yellow shirts and 2 blue shirts. How many shirts does Ali have? Well, we know how to do this. Clearly, Ali has 5 shirts, because 5 is 3 plus 2. If we let S be the set of yellow shirts and M be the set of blue shirts, then we can use the formula. The number of shirts which are either yellow or blue is 3 plus 2 or 5. Because these sets are discrete sets, in other words, there's no intersection between the 2 sets, because a shirt is either yellow or blue, we don't need to include the number of elements in S intersection M in our calculation. So all we're doing is 3 plus 2 is equal to 5. A slightly more difficult example. In a college, there are 8 students studying mathematics, 12 students studying physics, and 5 students who are enrolled in a joint chemistry, physics, and mathematics program. So that's 8 students who are just studying mathematics, 12 students who are just studying physics, and 5 students who are studying chemistry and physics and mathematics. The question is, how many students are studying either mathematics or physics? Let me re-say that. In total, 8 students are studying mathematics, but they might be some of them might be studying other subjects. 12 students are studying physics and maybe other subjects, and 5 students are studying chemistry and physics and mathematics. How many students are studying either maths or physics? In this example, if M is the set of students studying maths and F is the set of students studying physics, there's an overlap or an intersection between these 2 sets because some students are studying both maths and physics. So to calculate the number of students who are studying either maths or physics, we take the number of students who are studying maths, we add on the number of students who are studying physics, and then, so that we don't count the same students twice, we're going to subtract the number of students who are studying maths and physics. We put the numbers in. 8 who are studying maths, 12 are studying physics, 5 who are studying both maths and physics. We don't want to count these twice, so 8 plus 12 minus 5 gives us the answer 15. Next principle. Let's suppose we have two things we're counting, two operations, let's say. Let's suppose the first operation can be done in n ways, and second thing can be done in m ways. We multiply n by m to find the number of ways to do O1 followed by O2. For example, a man has 5 different shirts, 3 different ties, and 2 different pairs of trousers. How many ways can this person wear a shirt, tie, and a pair of trousers? So let's first he chooses a pair of trousers. He has 2 trousers. 2. Then he chooses a shirt. He has 5 choices for shirt, so 2 multiplied by 5. And then he chooses a tie. He has 3 ties. Multiply these two numbers together. He has 30 choices of outfit. Next example. 4 cities, Aberdeen, Birmingham, Coventry, and Derby, are joined by roads as shown above. By how many different routes can a vehicle travel from A to D without going back on itself? To answer this, first of all, if we're going from A to D, we must pass through either B or C. First of all, let's look at the left picture. Let's suppose we go from A to B and then from B to D. From A to B, there are 4 roads. From B to D, there's 1 road. So if we're going from A to D via B, there must be 4 multiplied by 1, or 4 different routes. Next, look at the right picture. Let's suppose we go from A to C and then from C to D. From A to C, there's 2 roads. From C to D, there are 3 roads. That means there must be 2 multiplied by 3 equal to 6 different ways to travel from A to D going through C. Add these 2 numbers together. The number of different routes from A to D must be 10. Next example. How many divisors does 2,800 have? The divisor is a natural number which divides 2,800. So for example, I could do 2,800 divided by 2, and I would get 1,400. Therefore, 2 is a divisor of 2,800. To answer this, first we need the prime factorization of 2,800. Note first that 2,800 is 1 multiplied by 2, multiplied by 2, multiplied by 2, multiplied by 2, multiplied by 5, multiplied by 5, multiplied by 7, where apart from the 1, these are all prime numbers. And let's suppose we're trying to create a divisor of 2,800. To create a divisor, we're going to use some of these numbers. We're going to use some of the numbers 2, 2, 2, 2, 5, 5, and 7. So for example, let's suppose I decide I'm going to use 3 of the 2s and 1 of the 5s. 2 multiplied by 2 multiplied by 2 multiplied by 5 would give it a divisor. Or I might decide I'm only going to use 2 of the 2's and 1 of the 5's. Or I might decide to use all of the 2's, none of the 5's, and 1 of the 7's, etc. How many different choices do we have? Just looking at the number 2's, I could have 0 2's, or 1 2, or 2 2's, or 3 2's, or all 4 of the 2's. We count from 0 to 4, that's 1 2 3 4 5. There's 5 different choices of how many 2's we use. For the 5's, I might use none of the 5's, or 1 of the 5, or both of the 5's. Means I have 3 choices of how many 5's to use. And for the 7's, I can either use the 7 or I don't use the 7. So that means I have 2 choices of how many 7's to use. Multiply these numbers together and we get 30. The answer is that there are 30 divisors of 2,800. And in fact, we could write these numbers in a list. The divisors of 2,800 are 1, 2, 4, 5, 7, etc. In general, we have a formula. Let's suppose that P1 up to Pn are prime numbers, and suppose that a number x is P1 to the power K1. There's a typo here. Multiplied by P2 to the power Kn, multiplied by P3 to the power K3, etc. Then this number x has K1 plus 1, K2 plus 2, etc. divisors. That's the end of the first chapter. Now we're going to move on to some more advanced counting methods. We're going to talk about permutations and combinations. In this chapter, we're going to need something called a factorial. We write a factorial using n exclamation mark. So, for example, 3 factorial means 3 times 2 times 1. Or 5 factorial means 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1, etc. There's one more factorial we need, 0 factorial. Just to make things work when we do more advanced maths, we need 0 factorial to be also equal to 1. Some examples very quickly. 4 factorial means 4 multiplied by 3 multiplied by 2 multiplied by 1, or 24. 7 factorial divided by 5 factorial. That's 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 5 factorial. Or I could write this as 7 times 6 times 5 factorial divided by 5 factorial. Cancel the 5 factorials and we get the number 42. Or we're going to be calculating things such as 52 factorial divided by 5 factorial, 47 factorial. And you can check if we calculate this, we get 2,598,960. Note factorial big very, very quickly. For example, 5 factorial is 120. 10 factorial is over 3 million. Just increasing from 5 to 10, and yet we've increased from 120 to more than 3 million. 15 factorial is more than a English billion or an American trillion? Now that we have factorials, we can move on to talking about permutations. Let's imagine that we have 4 pictures to arrange on a wall. How many different ways are there to arrange them? Here are my 4 picture frames, and I have 4 different pictures to put in the picture frames. For example, I might do it like this: Bugs, Daffy, Taz, and Tweety. Or let's suppose that I swap the final 2. Bugs, Daffy, Tweety, and Taz. That's 2 ways so far. Or a third way of doing this could be Bugs, Taz, Daffy, Tweety. Or a 4th way of doing this, a 5th way of doing this, a 6th way of doing this, 7th, etc. The question is, how many different ways are there to arrange these 4 pictures? So let's count. Instead of making a huge list of these, let's try to understand what's going on. Let's suppose we're choosing a picture to put in the first picture frame. We have 4 pictures and we're going to put 1 of them in. We have 4 choices for the first picture frame. And then we move on to the second picture frame. Now we have 3 pictures to choose from. We're going to choose 1 of these 3 pictures. So far we have 4 multiplied by 3 choices. Move on to the next picture frame. There's 2 pictures left. We have 2 choices of which picture to put in. So far we have 4 multiplied by 3 multiplied by 2 choices. And then finally, we have 1 picture to put in the final picture frame. So 4 multiplied by 3 multiplied by 2 multiplied by 1, or 4 factorial, or 24 different ways to arrange these 4 pictures. This is called a permutation. Permutation of a set of distinct objects is an arrangement of the objects in a specific order without repetition, without repeating the same object that we've already used. The number of permutations can be written in 2 different ways. We can either write NPN or we can write P bracket N comma N. I'm going to use this first notation because this is more internationally standard. And we have a theorem. NPN, the number of arranging n objects, is equal to n factorial. In the previous example, we had 4 objects, and there were 4 factorial ways of choosing an ordering of them. Now let's suppose that we still have 4 pictures, but we only want to hang 2 of them. How many ways are there to hang 2 pictures out of 4 pictures? This time I'm going to count them. Let's suppose we do Bugs and Daffy, Bugs and Taz, Bugs and Tweety. That's 3 so far. Daffy and Bugs, Daffy and Taz, Daffy and Tweety, etc. That's 6, 7, 8, 9, 10, 11, 12. I can count there are 12 different ways of doing this. But I don't want to have to make a list each time and count them. I want to have a formula. Let's understand this. First, let's suppose we're choosing the left picture. We have 4 pictures to put in. We choose one of these 4 pictures and we put it in the picture frame. And then we move to the second picture frame. We've got 3 pictures left. We need to put one of these pictures in the picture frame. We have 3 choices. That means there's 4 multiplied by 3, or 12 different ways to hang 2 pictures out of 4. How can we write this in terms of n factorial? There's 12 different ways to hang our pictures because 12 is 4 multiplied by 3. 4 multiplied by 3 is the same as 4 multiplied by 3 multiplied by 2 multiplied by 1 divided by 2 multiplied by 1. So we could write this as 4 factorial divided by 2 factorial. We have 4 pictures and we're choosing 2. NPR is the number of ways to arrange R objects which we choose from N objects. If we start with N objects and we choose R of them and arrange them in as many different ways as we can, how many ways are there of doing this? We write this as NPR. For example, let's suppose we have 3 objects, which we're going to call A, B, and C, and suppose that we take R of the objects. First of all, if we have 3 objects, we just take one of the objects. We could take A, or we could take B, or we could take C. P1, how many ways of permuting 1 from 3? We can see that the answer is E3. Next, let's suppose that from our 3 objects, we take 2 objects and we arrange them in all the possible ways. We could take AB or AC or BA or BC or CA or CB. 3P2, the number of ways of arranging 2 objects taken from a total of 3 objects, we can see is equal to 6. Or let's suppose from our 3 objects, we take all 3 objects. How many ways are there of arranging them? ABC, ACB, BAC, BCA, CAB, or CBA. We can see that there are 6 ways of arranging 3 objects taken from a total of 3. We have a formula for NPR. The number of permutations of n distinct objects taken R at a time without repetition is n factorial divided by n minus R factorial, where R is any number between 1 and n, any natural number between 1 and n. I've written this formula at the top because we're going to use this now. Find the number of permutations of 16 objects taken 3 at the time. We're asked to calculate 16P3. So we calculate 16 factorial divided by 16 minus 3 factorial, or that's 16 factorial divided by 13 factorial, and we can calculate that this is 3,360. The second main topic in this chapter is the idea of combinations. For the first example, let's consider the Turkish national lottery. enter the Turkish National Lottery, we must select 6 numbers from a choice of 49. The question is, how many different ways are there of choosing 6 objects from 49 objects? First thing to say is the answer is not 49p6 because the order of the objects doesn't matter. When we enter the lottery, when we're waiting for the balls to come out of the machine, 28, 16, 9, 7, 35, 47 is the same as 7, 9, 16, 28, 35, 47. Doesn't matter which order the balls come out. All that matters is which balls come out of the machine. So we're not doing permutations for problems like this. Instead, we have something called a combination. Combination of a set of n distinct objects, taken r at a time without repetition, is an r element subset of the set of n objects. The key point for a combination is the arrangement or the order of the elements does not matter. For a permutation, the order mattered. For a combination, we don't care which way the objects are ordered. We only care in which objects we have. There are 3 typical ways to write the number of combinations of R objects taken from a total of n objects. I'm going to use the most standard notation, which is NCR. Some books you look in might use open bracket n over r open bracket, or if you're looking at a very old-fashioned textbook, you might see C n comma r. For example, let's suppose we have 3 objects, which we call A, B, and C, and let's suppose we take R of these objects. Now remember, we don't care the order of the objects. First of all, if we take one of the 3 objects, we can take A, or we could take B, or we could take C. We have 3 choices. 3C1 must be equal to 3. Or, let's suppose from the 3 objects we take 2 objects. We could take A and B, we could take A and C, or we could take B and C. Remember, the order of the objects doesn't matter, so BA is the same as AB. 3 choose 2, 3C2 must also be equal to 3. And finally, if we take all 3 of our objects, then we must have ABC. There's only one way of choosing 3 objects from a total of 3 objects. So 3C3, or 3 choose 3, is equal to 1. We have a formula for NCR. This is n factorial divided by n minus r factorial multiplied by r factorial. This is almost the same as the permutation formula, but we have an extra r factorial here because the order doesn't matter. Here's the formula at the top. Example. A collector has 20 different coins. How many ways can 6 coins be selected? There's a total of 20 coins, and we're going to choose 6 coins. So we have 20 choose 6. We put 20 and 6 into our formula. 20 factorial divided by 20 minus 6 factorial multiplied by 6 factorial. And when we calculate this, we get our answer 38,760. Now we're ready to answer the question about the National Lottery. There are 49 numbers in the lottery, and we need to choose 6 numbers. So we calculate 49, choose 6, and we find that there are almost 14 million different ways to choose 6 numbers from a total of 49 numbers. Before we go on, let me remind you of the formulae. For permutations, the number of permutations, NPR, is n factorial divided by n minus r factorial. For combinations, when the order does not matter, the number of combinations is NCR, which is given with this formula. For example, let's suppose we have 9 people, and we're going to do 2 different examples. First example, let's suppose we're going to choose a chairperson, and then we're going to choose a vice chairperson, and then we're going to choose a secretary. Assuming that any one person cannot hold more than one position, how many ways can we do this? And then in the second part, let's suppose that from these 9 people, we're going to choose a committee of 3 people. How many different ways can we choose a committee of 3 people from a total of 9 people? Here are my 9 people. We choose one of these 9 people to be the chairperson. There we go. After we've chosen the chairperson, we have 8 people left to choose a vice chairperson. And then finally, we must choose a secretary. We have 7 people remaining to choose the secretary. There must be 9 multiplied by 8 multiplied by 7 ways to choose a chairperson, a vice chairperson, and a secretary. Or we can answer this problem using permutations. The order is important because we're choosing the chairperson first, then we're choosing a vice chairperson, and then we're choosing the secretary. When the order is important, we use permutations. From 9 people, we're permuting 3 people. 9p3 is equal to 504. Part 2. Now let's suppose from these 9 people, we're going to choose 3 people to be on a committee. Here, the order we choose them doesn't matter. When the order doesn't matter, we use combinations. 9 choose 3 is equal to 84. There's 84 different ways to choose a committee of 3 people from 9. Let me remark that there are similarities and an important difference between permutations and combinations. They are similar in that both times we don't allow repetition. We don't allow one object to be repeated. The difference, the important difference is that if the order is important. If the order is important, we use permutations. If the order doesn't matter, we use combinations. Key skill to learn from this chapter is when do we use NPR and when do we use NCR? Next example is about cards, playing cards. In a standard deck of cards, there are 52 cards. 13 hearts, 13 clubs, 13 diamonds, and 13 spades. And the cards go ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then jack, queen, king. When we play cards, we often dealt some cards and we hold them in our hand. When we hold some cards in our hand, this is called a hand of cards. First question, how many 5-card hands have 2 kings and 3 aces? In other words, how many ways can we choose 5 cards from 52 cards and ensure that we have 2 kings and 3 aces? Part 2, how many 5-card hands have 2 clubs and 3 hearts? Part 3, how many 3-card hands have all cards from the same suit? Let's do the first one. How many 5-card hands have 2 kings and 3 aces? We need to use the multiplication principle and we need to use combinations. First, we need to choose 2 kings. In total, there are 4 kings in a deck of cards. So we're going to be choosing 2 kings from 4, or 4 choose 2. Then we need to get 3 aces from a total of 4 aces, or 4 choose 3. And then we're going to multiply these together. We're going to be doing 4 choose 2 for the kings multiplied by 4 choose 3 for the aces. And when we calculate this, we find 24. 24 5-card hands have 2 kings and 3 aces. How many 5-card hands have 2 clubs and 3 hearts? In total, there are 13 clubs, and we need to choose 2 of them. So we're doing 13 choose 2. And then for the hearts, in total there are 13 hearts, and we need to choose 3 of them. Multiply these 2 numbers together. 13 choose 2 multiplied by 13 choose 3. There are 22,308 5-card hands which have 2 clubs and 3 hearts. How many 3-card hands have all cards from the same suit? Remember that there are 13 cards in each suit. Let's start by looking just at the hearts. How can we get 3 cards which are all hearts? The answer is, if we're choosing 3 from 13, there are 13 choose 3 different ways to do this. 286 different ways to get 3 hearts. For clubs, the number should be the same. There's also 286 hands which have all clubs, 286 hands which have all diamonds, and 286 hands which are all spades. So the answer is 286 plus 286 plus 286 plus 286, or 4 multiplied by 286, 1,144 different free card hands have cards from the same suit. Next example. A bag contains 2 white balls and 3 red balls. In how many different ways can 3 balls be chosen if at least 1 ball must be white? Or if at least 1 ball is white, we can either have 1 white ball and 2 red balls, or we might have 2 white balls and 1 red ball. For the first type, getting 1 white ball and 2 red balls, that's 2 choose 1 white ball and 3 choose 2 red balls. For the second type, 2 choose 2 white balls and 3 choose 1 ways to get a red ball. Add these together to get our answer. 2 choose 1 multiplied by 3 choose 2 plus 2 choose 2 multiplied by 3 choose 1. The answer is none. You have 1 red ball, 1 blue ball, 1 green ball, and 3 orange balls. The 3 orange balls are identical. How many visually different ways are there to arrange the balls in a line? If we had 6 balls which are all different colors, then this is going to be easy. The way to arrange 6 different balls would just be 6 Permute 6. But because we have 3 orange balls, the answer to our question is going to be less than this. For example, if we labeled the balls R, B, G, O1, O2, O3 for the red, blue, green, and the 3 orange balls, then these 2 orders, red, green, orange 1, orange 2, blue, orange 3, and red, green, orange 2, orange 3, blue, orange 1, would look the same. But if we did 6P6, we would be counting this twice. So we need to ask, how many different ways are there to rearrange the orange balls? And this is straightforward. Of course, there are 3P3 different ways to arrange these 3 orange balls. That means that if we calculated 6P6, we would be counting 6 times too many times. So the answer to this problem is 6P6 divided by 3P3. 6P6 is the number of ways to arrange 6 different balls, and then so that we don't count the same combination too many times, we divide by 3P3 the number of different ways to arrange the orange balls. The answer to this problem is 120. Another example. In how many different ways can the letters of the word mathematics be arranged such that the vowels are always consecutive, or to say it a different way, such that the vowels are always next to each other? The word mathematics has 11 letters, 4 vowels, and 7 consonants. And the rule is that these 4 vowels must always be next to each other. To answer this problem, we're going to consider these vowels as a single object. So in other words, instead of thinking of this as 11 objects, we're instead going to think of this problem as having 8 objects. MTH, MTCS, and then all of the vowels together. Of these 8 objects, we have 2 M's. We also have 2 T's, 1 H, 1 C, 1 S, and 1 vowels, A, E, A, I. So the number of ways to arrange these 8 objects. If we had 8 different objects, that would be 8p3. But because we have 2 T's, we must divide by 2p2. And we also have 2 M's, so we must also divide by 2p2. There are 10,080 different ways to arrange these 8 objects. We're not finished yet because we still need to look at the vowels. Next, we need to ask, how many different ways can the vowels A, E, A, I be rearranged? We've got 2 letter A, 1 letter E, and 1 I. If we had 4 different vowels, it would be 4p. But because we have 2 letter A's, we need to divide 2. There are 12 different ways to arrange the vowels. To finish the question, we multiply these 2 numbers together. 10,080 multiplied by 12 gives 120,960 different ways to arrange these letters such that the vowels are consecutive. Before I finish this chapter, if you have a scientific calculator, have a look for permutations and combinations on the calculator. This is a picture of a Casio calculator. You can see that NPR on this calculator is on the multiplication button and NCR is on the division button. Perhaps the best calculator on the web or smartphone app is Wolfram Alpha. If you're using wolframalpha.com or Wolfram Alpha app to do maths, try typing 7 permute 3 or 7 choose 3 into Wolfram Alpha and see what you get. Before I start talking about probability, I'm going to take a 5-minute break. Now let's continue. For the final 15 or 20 minutes of today's lesson, we're going to talk about probability. Most of the probability topics we would be talking about next week, but I want to do the introduction this week. Let's suppose we roll a single die. What are the possible outcomes? We might get a 1, we might get a 2, we might get a 3, we might get a 4, we might get a 5, we might get a 6. The set of all of the possible outcomes of some experiment is called a sample space. And each of the numbers in S, or the elements in S, are called simple events. Now let's suppose that we want to roll an even number on our die. We're interested in 2 or 4 or 6. The set containing 2, 4, and 6 is called a compound event. Simple event means just one thing. Compound event means some set of simple events. More formally, the set S containing elements E1 up to En is called a sample space for some experiment if and only if the set S contains all of the possible outcomes of the experiment and one and only one of the elements in S must occur. An event is any subset of S, and we include the empty set and S itself. E subscript I is a simple event. The set capital E containing only one element is also called a simple event. The set E is called a compound event if E contains more than one element. Next, let's suppose that we have 2 dice. What are the possible outcomes from rolling 2 dice? For the first die, we might get 1, 2, 3, 4, 5, or 6. For the second die, again, we might get 1, 2, 3, 4, 5, and 6. So all of the possible outcomes of rolling 2 dice are written here. We might get a 1 and a 1, or a 1 and a 2, or a 1 and a 3, a 1 and a 4, etc. We might get a 2 on the first die, a 1 on the second die, or a 2 and a 2, a 2 and a 3, etc. In total, there are 36 different outcomes from rolling the 2 dice. For example, if we're rolling 2 dice, then the sample space is the set of all pairs A and B, where each of A and B is a number between 1 and 6. And then we're asked about some compound events. What is the event which corresponds to a total score of 7? How can we get 7 from rolling 2 dice? We might have a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, or a 6 and a 1. The event which corresponds to a total score of 7 is the set containing these 6 pairs. Or let's suppose we're asked, what is the event which corresponds to a total score of 3? To get a score of 3, we're going to have either a 1 and a 2, or a 2 and a 1. So we're looking for the event, which is the set containing 1, 2, and 2, 1. What is the event which corresponds to a total score greater than 10? How can we get a score which is greater than 10? We could have 5 and 6, 6 and 5, or 6 and 6. And finally, what is the event which corresponds to a total score of 2? We must have 1, 1. Now let's define probability. Let's suppose we have a sample space which contains n simple elements. The probability of event EI is a number P of EI, which needs to satisfy 2 rules. Rule number 1, the probability of EI must be a real number in the closed interval from 0 to 1. The second rule is that the probability of E1 plus the probability of E2 plus the probability of E3 plus ... plus the probability of En must be equal to 1. For example, let's suppose we're flipping a single coin. Then the sample space, all of the possible outcomes of flipping a single coin, we might have a head or we might get a tail. So the sample space is the set containing heads or tails. It's fair to assume that we have a fair coin. So the probability of getting a head is a half. The probability of getting a tail is also a half. You will note that the probability of getting a head is between 0 and 1, and the probability of getting a tail is also between 0 and 1. So the first rule is satisfied. And you will notice that if we add these together, probability of getting a head plus the probability of getting a tail is a half plus a half, or 1. So the second rule is also satisfied. If we flip this coin 1,000 times, we would expect to get head roughly 500 times. Probably not exactly 500 times, but roughly 500 times. The probability of an event, which we write as P of E, must satisfy these 4 rules. The probability of the empty set must be 0. The probability of sample space S must be 1, because something in the sample space always happens. If we have a simple event, then the probability of capital E must be the probability of small e of I. And if E is a compound event, then the probability of E must be equal to the sum of the probabilities of all the simple events. For example, if E is the compound event containing A, B, and C, then the probability of E must be the probability of A plus the probability of B plus the probability of C. Let me remark that if we have P of E is equal to 1, that means E is certain to occur. If we have the probability of E is equal to 0, that means E will never occur. Now let's suppose we're flipping 2 coins. What is the sample space of flipping 2 coins? We might have head-head, we might have head-tail, we might have tail-head, and we might have tail-tail. And it's fair to assume that the probability of each of these is 1/4. 5 questions. What is the probability of getting one head and one tail? What is the probability of getting at least one tail? What is the probability of getting at least one head or at least one tail? What is the probability of getting 2 tails? What is the probability of getting 3 tails? First of all, how can we get one head and one tail? We could either have head tail or we could have tail head. The probability of getting one head and one tail must be 1/4 plus 1/4 or 1/2. How can we have at least one tail? We might have head tail or tail head or tail tail. The probability of getting at least one tail must be 3/4. How can we get at least one head or at least one tail? Head head has at least one head. Head tail has at least one head. Tail head has at least one head. Tail tail has at least one tail. In fact, we have all of S, and the probability of all of S is equal to 1. We are certain to get at least one head or at least one tail. What is the probability of getting 2 tails? We must have TT. The probability of getting 2 tails is 1/4. What is the probability of getting 3 tails? It's not possible to get 3 tails from flipping 2 coins, so our compound event is the empty set, and the probability of the empty set is equal to 0. A theorem. If we assume that each simple event in S is equally likely, then the probability of an event E occurring is equal to the number of elements in E divided by the number of elements in S. Or using the notation from Combinatorics, NE divided by NS. Let's go back to 2 dice. So suppose we're rolling 2 dice, and let's suppose that each simple event is equally likely. Find the probabilities of the following: a total score of 7, total score of 3, a total score greater than 10, total score of 2. First of all, total score of 7. We've already found this compound event. The number of elements in this compound event is 6. The number of elements in the sample space is 36. So the probability of getting a 7 must be 1 divided by 6. What is the probability of getting a total score of 3? Again, we've already found this compound event. This compound event contains 2 elements. So we're doing 2 divided by 36 or 1 divided by 18. The probability of getting a total score of 3 is 1 divided by 18. What is the probability of getting a total score which is greater than 10? Using the same idea, we can calculate that probability is 3 divided by 36 or 1 divided by 12. What is the probability of getting a total score equal to 2? The probability is equal to 1 divided by 36. And one final example. You randomly draw 5 cards from a standard deck of 52 cards. What is the probability of getting 2 clubs and 3 hearts. First of all, how many different 5-card hands are there? There are 52 choose 5 different possible 5-card hands. So the number of elements in the sample space must be 52 choose 5. We've previously calculated the number of 5-card hands which have 2 clubs and 3 hearts. To get the 2 clubs, it was 13 choose 2. To get the 3 hearts, it was 13 choose 3. So the number of elements in E is 13 choose 2 multiplied by 13 choose 3. Each one of these events is equally likely. So the probability of our event is the number of elements in E divided by the number of elements in S. We are calculating 13 choose 2 divided by 13 choose 3 divided by 52 choose 5. And when we calculate this, we get 78 multiplied by 208 divided by 2,598,960. And this is approximately equal to 0.00662 to 2 significant figures. This, of course, goes on and on and on. I'm just interested in the first 2 numbers. It's called writing this as 2 significant figures. I can't write this. Here we go. Lots of zeros followed by 2 numbers is called writing this as 2 significant figures. And that's the end of today's lesson. Next week, we will continue talking about probability. 2 weeks' time, there's no lesson because we will have a midterm exam. And then in 3 weeks' time, we will talk about graph theory. Do you have any questions? When you say problem 8.4, do you mean in the lecture notes? Okay, give me a few seconds to put this up on the screen. Okay, so I'm guessing you're talking about problem 9.4, hyperbola. Find the foci of x squared minus y squared is equal to what? Last one, D. A hyperbola has foci at plus or minus 10, 0, and vertices at plus or minus 6, 0. Find an equation for the hyperbola. So let's see, what do we have? So we must have something like this. 0.60, minus 60, and foci at 10, 0, and minus 10, 0. We can also write down the center to focus distance, right? This is the center, this is the focus. The center to focus distance must be 10. The vertices are at plus or minus A0. So just from this picture, we can see that A must be 6 and C must be 10. Okay, now I'm going back to the page which tells us about hyperbola. Looking at the left picture, the equation is x squared a squared minus y squared b squared is equal to 1. But I can't write on this one. The left picture, we have this equation. Can I get my whiteboard back? No, it's gone. Here's the equation, x squared over a squared minus y squared over b squared is equal to 1. We know that a is equal to 6, and we know that c is equal to 10. We don't know b yet. But we do know that c is equal to the square root of a squared minus or plus b squared. Using this formula, putting in 6 and 10, and then rearranging, we can find b. After we find b, we can put a and b into the standard equation and finish the answer. So let me rearrange. That would be b squared is c squared minus a squared, or 100 minus 36 is 64. B must be 8. So I'm running out of space. Let me write it in the middle. X squared divided by a squared is x squared divided by 36. And then y squared divided by b squared is y squared divided by 64. You're welcome. Are there any more questions? For the exam, you should focus on everything that there's no one topic to focus on. I will ask questions about geometry. I'll ask questions about combinatorics and probability. So focus on part 2 and part 3. Part 2, geometry. Part 3, combinatorics and probability. How will the exam be? I'm going to ask 3 questions, and I'm going to give you 30 minutes each question. And you will receive the questions at delays. So at the time of the exam, you will receive question 1. You have 30 minutes to answer question 1. You'll write your answer on a piece of paper, take a picture of your paper or scan it to create a file, and then upload that file into the OLearn system. And then 30 minutes after the start of the exam, question 2 will be revealed to you. And again, you'll have 30 minutes to solve that question. And then 30 minutes later, you'll get the third question. And again, you'll have 30 minutes to solve that one. I'll write an email sometime this week or just the start of the following week, in which I tell you the exact topics and exact details about the exam, because I haven't written the exam yet. I might still change my mind. Yes, it's 3 questions. Each question you will have 30 minutes. So in total, there will be 90 minutes of exam. I didn't send an email yet. I will send an email in the next 7, 8, 9 days. I want to write the exam first, and then I will send the email so that I'm sure that the information in the email is accurate.